My name is Greg Newmark. I'm the chapter and secretary of the Chicago chapter ACM this year. And our other two officers are also here this evening. Alvin Chin, here, our vice chair, and Valentina, who's currently downstairs welcoming people, but she'll be up in a moment. The Chicago chapter of the ACM is a professional chapter of International ACM, the Association for Computing Machinery, which tells you how long it's been around. Actually, the Chicago chapter has been having monthly meetings throughout the academic year here in Chicago for over 50 years. I believe we're the longest continuously running professional chapter in the system, something that we're proud of. You can join National ACM, of course. You can also join our chapter. There's some forms at the table there. It's only like $4 right now, or you can just give a donations, keep the snacks going and stuff. We are going to do a drawing tonight in the fishbowl there, if you put your business card in, for a National ACM membership. That's normally $100 a year, so that's a good deal. That gets you a variety of online resources and the magazine of the ACM. We are working on our February meeting, but our next for sure meeting will be in March, and it'll actually be at the Loyola Lakeshore campus, which is a bit north of here, but you take the red line right up there. And that will be a speaker from the ACM Distinguished Speakers Program, and those are usually really good. We try to do one of those every year or so. And the National ACM and the chapter splits the cost of getting a real professional speaker in. And that will be, I believe, in the intersection of machine learning and program testing.
Yeah, software reliability, software engineering.
And of course, if you've joined the meetup, you'll get that announcement as soon as we post that. So we'll do the drawing at the end of the meeting. Feel free to take the snacks and the drinks. And the closest bathrooms that are open, I believe, are on the 5th floor. So you can take the elevator down to that. With that, I'll have Mark. Hi, Mark. Mark's here. Oh, I also wanted to point out that we're able to meet in this room at Loyola for free because the Loyola Computer Science Department sponsors us. And we do have Ron Greenberg here, who's a professor, computer science professor at Loyola, who's our official contact with the university. And we've been happily holding meetings here at Loyola for many years now, and getting some great meeting spaces. Okay, Alvin will now introduce our speaker. Thank you.
Okay, so before actually I do so, to get notice of the ACM meetups, we have, of course, the ACM, the meetup website. We also are on Facebook and Twitter. You also go to like chicagoacm.org. We will also announce things there too as well. We also have Twitter too as well, and LinkedIn, so you can check those sites there to figure out the next meetups. Also as well, if you register to become an ACM Chicago member, we also send through the email list as well, so you can also get that too as well. Before actually I introduce Mark here, our speaker for tonight, I just have a quick announcement from Frank Stawicki. You want to mention something regarding about some event so that you have?
Yeah. We also, I represent a group called March, and we're promoting artificial intelligence within the Chicago and Midwestern ecosystem. So what we are planning to do is we're planning to hold a large 2-day event in March. So if you go to our website, take a look. But before then, next week on the 22nd, we're going to have a half-day preview event. And we wanted to actually make sure we get that out in front of you. And if you run right now on your cell phones and you use this code ACM free on our website, you can get a free. There are 5 free tickets for the first people that get on there. Everyone else from this event, if you use the code ACM50, you'll get half-price tickets. We'll also be posting this information on the meetup site as well. So it's Chicago AI Days. Half-day event. We'll have speakers from GE, Pfizer, and a variety of other major companies. A women's panel, as well as cross-track panels affecting AI across multiple industries and social good. Any quick questions? That's ACM3, ACM50. Thank you.
All right, thank you, Frank. Okay, so with that, the reason why you're all here for is our first meetup of 2019 for January. So we're very, very pleased to have Mark Shapiro from Anthem. And it's good that he actually was able to come on short notice, because originally you might have noticed on our meetup site that Playman Petrov, the kind of director or VP of AI, so unfortunately he had a business commitment and trip he had to go to. So very good that he was able to recommend Mark in his place to come give the talk tonight. So the talk he's going to talk about is about trends and applications of artificial intelligence in healthcare. There's lots of AI happening in healthcare. So a little bit about himself. He's a principal AI engineer at Anthem. He plays a critical leadership role contributing to the journey Anthem is on, transforming healthcare with trusted and caring solutions, giving members access to the care they need. Prior to joining Anthem, Mark worked as a data scientist at Deloitte and later at Cogentix, a machine learning startup recently acquired by Accenture. Credentials: he has a PhD in electrical engineering from the University of Illinois at Chicago. Prior to moving to the industry as a data scientist, for over 10 years, Mark conducted neuroscience research in neurocontrol of human movement in healthy individuals and patients with movement disorders at UIC and Rehabilitation Institute of Chicago. So very, very good, lots of experience, and an expert on talking about this AI and for healthcare. So without further ado, please give a warm welcome to Mark Shapiro.
Thank you. And thank you, Alvin, for inviting. So this talk will be probably a little bit unusual for this group, because I will not be showing code, and it will be highly non-technical. It's more of an overview, and it may feel more like a journal club than a computer science meeting. But I hope that I will be able to give an overview of the major trends and ideas in digital healthcare, in particular from the point of view of clinicians. Because clinicians, in the end, is the key group that determines what is being used, how it's being used, what is being accepted. And when I started looking at it, I think it's really important, especially for anyone who is involved in digital medicine or in digital healthcare in one way or another, to understand that point of view. Now, I'm not a clinician. I did research in neuroscience, so I interacted with clinicians, but I'm not a clinician. So lots of statements, and most of the statements that are on the slides, are not mine. And I tried to put the quotation marks everywhere, and if not, most likely that's still a quote from some clinician from some article. So just to make sure that, well, these are not my opinion. So the factors that driving adoption of AI in clinical research and deep learning in digital medicine is digital imaging in all its forms becoming more powerful. And well, that's natural, because deep learning originated first and it showed its first sort of breakthrough success in image analysis, and then it's been evolving, and now it's been used in many more areas. Then digitization of health-related records is accelerating, and sharing of high-quality, fully labeled and specialized data sets is becoming a reality. So there is a number of very high volume data sets, and there's a FHIR, F-H-I-R, so it's a fast healthcare interpretational resource standard that would enable, ideally, a large-scale data sharing. Now, deep learning is highly adaptable to integrative analysis of heterogeneous data sets sampled from diverse sources, and that's building up on medical data, genomics data, and all other omics data plus demographics plus whatever data may be joined with kind of an underlying core medical data. Then another key factor is that it has capacity to inform the process of discovery in health research and facilitate hypothesis generation. And that may be, that is due primarily, as I understand, because with deep learning, you don't have a predefined set of features, like in essentially all the other algorithms. And so if you can run a deep learning algorithm and then identify which features from the data set were critical for generating particular decisions, that may lead in the end to uncovering associations that were not hypothesized from the start. Then it shows promise for streamlining routine work by healthcare professionals. Now, this is essentially the voice. All of these driving factors were taken from a viewpoint in JAMA. It's the Journal of American Medical Association. That's a flagship journal in medicine in the US. And this is the key, essentially. Well, the goal of the physicians is that they want more time to focus on the tasks that are uniquely human. They build relationships with patients, exercising empathy, and using human judgment to guide and advise. And that topic will be recurrent, and it will show up in many other contexts later on. So that the idea is that digital medicine, the goal of digital medicine is to enable physicians to relate to patients and to determine the treatment here, and not to replace. Now, it's diffusing rapidly through combination of open source and proprietary programs. Well, I don't think any comment needed. And none of these developments depend on improvements in the basic technology of deep learning. Now, that statement is actually the same as Jeff Hinton expressed in another viewpoint in the same issue of JAMA. And the idea, as I understand, is that the foundations are there. So there are obviously, there are developments and there are different iterations of various algorithms. But the fundamentals are already there and they're being used. And one of the challenges and opportunities is to figure out how to apply them. And so then, combined with variables, I will not focus on this. Remote monitoring, digital consultation, deep learning, other machine learning techniques can bypass the model of intermittent data collection, and that's been one of the problems that digital medicine is aimed to alleviate. That you get healthcare when you see it up. Well, you get some prescription or you get some medical treatment, and then as a patient, you go home, and then until the next visit or until something happens, you're essentially on your own. And the idea is to make it essentially continuous. So the factors, as they apply to a deep learning healthcare system, there are three essential. There are three essential elements. So one is digital knowledge base, then artificial intelligence analysis, and the final one that's related to physicians. It's the synthesized results for recommendation. So the idea is that whatever is done in that context of digital medicine, in the end, is to enable a clinician to make a decision. And it's been put even more forcefully and more directly by in another viewpoint in a different issue of JAMA. That the goal is to design a clinical decision support system that will be used by clinicians, and that will, instead of replace the clinician, it will enable and kind of expand care. And so they, well, one of the sentiments was, why do CDSS, or the clinical support systems designed to direct interactive use by clinicians, have challenges of credibility and adoption for over 40 years when lots of these algorithms have been showing very high accuracy? And so a couple of factors that from this particular point of view that is critically important to keep in mind when developing these applications. Black boxes are unacceptable. That's a very strong statement. I don't think that it can be hedged a little bit. Not every decision that a clinician makes can be totally explained. So there's intuition. There are lots of other factors, but overall, the demand is to explain why certain decisions made, and that's the reason why there's a very strong push for interpretable AI or explainable AI. Time is a scarce resource. So again, well, one of the complaints with the EHR, electronic health records, was that, well, with the introduction of EHR, clinicians now even have less time to interact with the patient. And so the idea, whenever new technology is introduced, that actually the aim is to free more time for the clinician to actually focus on interacting with the patient and care. Complexity, lack of usability, thwart use. Now, this time is a scarce resource, and the goal to design simple and easy to use interfaces it's universal. It's not just for deep learning applications in healthcare. It's for any devices or any algorithms that are designed in the end with the user in mind. Right? So relevance and insight are essential. So CDSS should reflect an understanding of the pertinent domain and the kinds of questions which clinicians are likely to want assistance. And that, so let's say there's a saying that, well, you need to treat others the way you want to be treated yourself. And there's another variation of that saying that you want to treat others the way they want to be treated. And so this is the same sentiment. Whatever we think we might design to help clinicians, it's very useful to actually ask directly. Okay, well, if you have this capability, I mean, what is the most important problem that you want to solve, or where would you want to get help? So, in other words, the design ideally is driven by the clinician demand, and then delivery of knowledge information must be respectful. When I read it first, well, I was a little bit surprised, but then it's kind of obvious. If you design an application, and then you go to an ophthalmologist and say, okay, well, here's the digital ophthalmologist. The chances of that particular physician accepting that particular device or algorithm are a little bit lower than if you said, okay, well, this is something that will help you. And scientific foundation must be strong. Well, it should have rigorous peer-reviewed scientific evidence establishing safety, validity, reproducibility, usability, reliability, and all that. So this is important because later on I will show reviews, and there's a very strong opinion that the clinicians pay attention to studies that are published in peer-reviewed journals, that where clinicians or doctors were part of that study from the beginning, or at the very least, well, they were asked to review the results, and there are certain steps are taken to establish its validity and reproducibility. And then once it's published, and then even when it gets an FDA approval, that's the beginning of the process that in the end may or may not result in wide acceptance. So the potential roles of AI-based technologies in healthcare. The focus will be on saying diagnostics. Let's say that image data and deep learning, that will be the probably the focus of that talk. review studies. And in therapeutics, well, data-driven precision medicine. That is another focus that I will not. I don't think that I will mention much in this talk, but this is in fact focus in the January issue of Nature Medicine on digital medicine, and there's another issue of National Geographic that has a focus on precision medicine. So the studies that I review here and the talk is actually made much simpler by an excellent review in that issue of Nature Medicine by Eric Topol. He's a physician, he's a cardiologist, geneticist, served as chairman of cardiovascular medicine at Cleveland Clinic. Then he founded College of Medicine, and then in 2006 founded the Scripps Translational Science Institute at La Jolla, and he's running a significant part of the precision medicine initiative right now. He published a couple of books. The last one in 2015 was The Patient Will See You Now, and in March of 2019 there's another book coming on deep medicine. And again, well, the sentiment that he is very strongly expressing is that the goal is to free physicians from the tasks that interfere with human connection. It's not to replace physicians by any means. And so the goal is that for AI to create space for the real healing that takes place between a doctor who can listen and a patient who needs to be heard. So that's essentially the gist of the whole effort. And so Eric Topol published a review, and I could just go through the chapters of his review in that issue. Well, the issue itself is a treasure trove of information on digital medicine. So I'm just sort of skimming the surface of what's all there. And he goes by specialties. So ophthalmology is probably, well, it's probably the most obvious on the one hand, because the specialty to get applications of deep learning, and it also showed the earliest success stories, in particular in diagnosing diabetic retinopathy. And in one of the studies, just going back to the idea that it should be explainable, well, the patient can watch a video during the exam that shows what portions of scan were used to reach the algorithm's conclusion, which is very cool. And that improves the acceptance and the adherence to the recommendations that physicians takes afterwards. It increases trust. So it's good all around. And another somewhat surprising, for me at least, was the idea was that the eye, on the one hand, well, it's our window to the world, but on the other hand, well, the eye provides a very it's a very interesting window into the state of the body. So there are many applications in which the eye exam leads in the end to diagnosing conditions with cardiovascular system, with the blood pressure, smoking, hemoglobin. There's an app that I saw recently that they take a photograph of the retina, and the idea is to see if there's a abnormal function of the liver judging by the color. Well, not the retina, just the picture of the eye. So one of the examples of deep learning, application of deep learning in ophthalmology is with transfer learning. So with deep learning, the idea is that, well, you need enormous amount of data to train a model. And in this particular case, the focus, well, first of all, that's a clinical decision support algorithm that that's consistent with the whole idea. Well, the goal is to design the clinical decision support system in whatever way. Now, there's a lot of interest in it because, well, there are 30 million scans of retina performed each year worldwide. That's an enormous amount of work. There's a large population of people that are affected by these conditions, and so obviously there's a very strong interest in trying to cure it. So the data they obtained about 200,000 images, of which 100,000 images were taken we used an analysis from 4,700 patients, and this is not, well, it's just 100,000 images, but the key here was that they took the trained ImageNet and then used transfer layers. So they stripped they retrained the last layer. So the last, these are softmax layers, and then the inner weights that take the most effort to train were taken as is. And so there's a different input. They classified it on 4 outputs and using labeled data, and achieved very impressive accuracy. So the AUC 99.9%, the accuracy 96.6 sensitivity in this. So it's extremely impressive. Now they also compare it with the human experts, and the human experts were on average. There's a weighted error. They were slightly better, but again, there was a pretty large range. So the human error was between probably 3-4%, all the way up to 10% sometimes. But on average, it was slightly better than the net. And another thing the authors did was they tried the same approach, but used 1,000 images. I mean, this is basically nothing when you train a deep learning net. And again, well, because it's transfer learning, not full training, the AUC was still 98.9%, and accuracy very high, although the error went up a little bit. Another step here, well, towards explainable AI. The way they try to understand how the network came up with a particular classification. In this case, they occluded images in different portions of the images, and then saw which ones actually influence the output the most. So that was one of the methods that they were able to explain the results. Radiology, essentially it's a CT scans, chest X-rays, mammography, and wrist X-ray. And again, well, chest X-rays are the most common type of medical scans. It's over 2 billion worldwide. So anything that can improve that or make it more efficient or cost-effective is going to have a big impact. And yet the comment by the physician, that comment that I put here, that one algorithm was compared that of 4 radiologists. The conclusion was the algorithm outperformed. On the other hand, well, the AUC is far from optimal. The sentiment was that the test was not what radiologists actually do. And in the end, well, there's a very strong statement that field clearly is far from demonstrating very high reproducible machine accuracy. And that's surprising. On the other hand, well, that was based on the data up to probably August, and in the same issue, in December there was another study published that got much better results. So in these particular ones, so the idea was to detect acute intracranial hemorrhage. So there's a stroke. So there are 2 types of stroke. One is hemorrhagic stroke, and the other is ischemic. And it's extremely important to be able to identify which is which when the patient gets into ER, because that determines the treatment, and the treatment is totally different for two cases. And the key thing here was that, first of all, there are very few cases. There are 904 cases that the researcher used to train the net. One, and secondly, they introduced the idea to get the explainable results. They introduced the idea. They created an atlas from the input data, and they also created kind of features that they deemed to be important. And in the end, when there was a result, that result was accompanied by a particular set of features from the atlas of scans that led to that diagnosis, or that led to the decision. And they used, ImageNet and a combination of 4 off-the-shelf trained networks, network architectures. Dermatology, again, there are skin cancers, melanoma, and skin lesions. Again, the clinician's perspective was that, critique was that studies were not conducted in clinical setting in which a doctor would perform physical inspection and shoulder the responsibility for an accurate diagnosis. Well, yes, that's true, but still, it's interesting that most skin lesions are diagnosed by primary care doctors, which means, though, that the bar is actually a little bit lower, because the goal is to make the primary care physician better diagnose a potential problem and then refer to a trained dermatologist. So, in other words, the algorithm doesn't have to outperform. It would be nice if it did, but it doesn't have to outperform a trained dermatologist. But the goal is, at least, is to improve the diagnostic capabilities of primary care physicians. Another thing for dermatology, there's an app. There's a site, actually, modelderm.com. So you go to the site, and you can take a picture with an iPhone of a skin region that you would want to analyze. Well, you upload it there, and then you get the the diagnosis, but you get some suggestions of what it could be. And so the idea is that again, it's very promising. And the comment from physicians was, it's unclear whether the site is designed for patients, non-specialist clinicians, or dermatologists. And in particular, if that's designed for mainly with patients in mind, then it's not clear how to interpret the suggestion. Okay, well, there is a 0.02 probability of melanoma. What does it mean? Do you have to run to the dermatologist, or you can just forget about it? On the other hand, another comment is that that same site and that same type of app can be very useful for a primary care physician or for a dermatologist. Now, an example paper in also in JAMA Dermatology in December 2018. So it's very recent. That's a non-pigmented skin cancer by the research used CNN. They used 8,000 dermoscopic. It's a handheld device that takes a kind of high resolution image, and then there are 6,000 close-up images. So the data collected by one physician in Australia between 2008 and 17, so about 10 years. It's validated. And CNN. Well, that's interesting here was that they had I think they had 95 raters who also rated the same images, and these raters were dermatologists with less than 3 years experience, 3 to 10 years experience, and over 10 years experience. And so the CNN outperformed specialists with less than 10 years experience, but more experienced clinicians outperformed it still. So that's one comment there. And another, I put this table, I don't know if you can see the numbers there, but the data set is highly imbalanced. So there are cases with a lot of types of lesions with a lot of cases, and there are some with very few. And then when they tested it, then the model actually failed in a couple of less represented cases, and obviously it could not recognize whatever lesion it was presented if it was not trained on it. So in other words, it's local. You in the end, well, it will perform on what it's trained. But again, well, they used off-the-shelf versions of deep learning networks. Cardiology, well, it's cardiography and EKG. With EKG, there are rule-based algorithms with not very high accuracy. On the other hand, in that issue of Nature Medicine in 2019, there were 2 studies. So one was screening for cardiac contractile dysfunction, and I think both. Well, that was done at Mass General Hospital in Boston. It's a massive. No, it's in my clinic. Okay, so there's a massive number of patients. It's 625,000 patients screened, and then almost 100,000 were selected for the analysis. Now that was 12-lead EKG, so it's a 12-lead signal that was taken as a picture, and then it was analyzed. And again, the AUC 0.93 sensitivity, specificity, everything was very high. At the same time, the comment was in Nature Medicine, there is news and there are comments by other researchers. And for that paper was that there were some false negatives that were important. And so unless the algorithm improves on that, they missed a number of cases that would have been identified by trained cardiologists. And so the comment was, well, it's impressive, but it needs to be worked on. And another one was Hanun et al. That's from Andrew Eng's group, and that is for ambulatory for detection of arrhythmia in ambulatory electrocardiogram. So this is for home monitoring, essentially. If that algorithm works, that can be well, the train weights can be put on an app, in an app, and then well, there are sensors now. Well, Apple Watch can measure EKG, one lead EKG. So that in the end may pave the way for EKG applications. And the comment there was that the algorithms, both of these actually, are not able to provide explanations for the pathophysiological basis of classification outcomes because they cannot reveal the functional dependencies between data inputs and classes, and because cardiologists use other very specific features in the EKG, so the QRS width, QT interval, there's a couple of others that these algorithms didn't use. So that seems to be like an opening for an improvement. So if there is more research, or there's more effort put in, or if these features are added to the algorithm somehow, looks like, well, that would be an opportunity. Pathology. So the goal here was, and there's an example of study that pathologists were given 129 test slides at less than a minute per slide, and then the CNN outperformed the pathologist. On the other hand, when with no time limit, well, pathologists outperformed the network. So the key here in the end is that it's a combination of pathologist and algorithm can save time for pathologists to review the slides. In other words, it makes it simpler and improves efficiency. Well, that would be a win. And again, it goes back to the idea that, well, it's a synergy of the combined, that synergy between the clinician and an algorithm. And the thing with pathology, so it appears to be a field that's tailor-made for deep learning applications because, well, there are images, and deep learning are great for image analysis. Well, the trick though is that there's enormous variety of conditions that pathologists diagnose, and so, well, we're talking about, well, hundreds, if not thousands, and so that means that, well, to train a network, you have to have a data set that would either include all of these potential cases, or that could be local. So in other words, well, there are the conditions only for particular organs. And then one can think about a library of deep learning, trained deep learning, pre-trained deep learning algorithms that would be called on demand. So if I can think of that, well, if pathologists will see a particular slide with a skin, well, potential skin cancer, that would be called a skin analysis algorithm. So something like that. But as of now, it's a highly it's a fast developing field, but it's under development. Gastroenterology. Well, that's an interesting case. So the paper here was from Mori in Japan. They actually created, I don't know how well you can see it. So they created a system that was put side by side with the gastroenterologist who was doing a colonoscopy. And so, so the gastroenterologist, when he wanted, he could take a picture, and that picture would be analyzed by the algorithm right there in real time, and then it would immediately give a suggestion. So there is a whatever 95% probability that it's that micro polyp that the gastroenterologist is looking at is one kind or another. And actually, well, they have a video on site, well, as a supplement to this paper. Look at it. So now it's just a selection. It's not a summary, but it's a selection of some applications and the number of cases that were considered for deep learning algorithms, and the range is vast. Well, you go from 1,000 to about 700,000 samples to train and test the algorithm. AUC is, well, you can get very high, or it can go a bit lower. One of the important comments in the literature is that AUC, the area under the receiver, under the curve of receiver operating characteristic, may not be the best and most informative metric. And the comment was that it doesn't reflect the true probability. And yes, the output softmax layer converts in classification. Well, it converts the values to between 0 and 1, but that doesn't reflect the true probability of whatever the cases are being classified. And there is a debate in the literature, and if somebody is interested, I can give you the resources. And so, well, you get AUC, then you get specificity, sensitivity, specificity, you get accuracy, you get F1 measure, and then depending on the condition, you can get well, more attention can be put on false negative or false positive rates. So in the end, well, Topol gives an analogy between the self-driving cars and medicine, and well, the font is somewhat small, but the level 0 is, well, no automation. Now, level 1 is what we get more or less right now very often when there is a car that's equipped with the lane following technology. Or, well, cruise control would be this one. Now, level 2 is partial automation. And then we get the system automation. And his view is that level 5 full automation, where clinician is not in the picture, is not the goal at all. Even level 4 high automation for medicine specifically. Healthcare, well, there are other aspects of healthcare where the idea is just to maybe to not to minimize, but to determine if the clinician is not really, doesn't have to be involved, then it's better not to contact. Well, if you get a Tylenol and get well, then there is no need to schedule an appointment. And the goal, it looks like the goal for, at least for now, is level 2, when there is partial automation, and which is the clinical decision support system, in which, well, there's a very, in which there's a synergy between the deep learning technologies and clinicians. Now, regulatory environment. Well, that's kind of important. So conventional medical devices go through FDA, and they get approvals of class 1, 2, or 3. Well, the higher the number, the more stringent requirements. And FDA recently introduced the new program. So the AI-based technologies are encompassed by the term software as a medical device. And the criteria and the whole protocol for getting an FDA approval for software as a medical device is different. It's streamlined, it's more efficient, so it's tailored for AI. And FDA has developed a software pre-certification program that's actually targeted not a specific algorithm, but rather at companies that are developing these algorithms. In other words, if a company has established credentials, then it gets more or less a fast track, as I understand. So the workflow is, well, they check FDA pre-certification level, then evaluate software as medical device. If it's low risk, then exception, and then commercial distribution and real world use. And then that's the last point in the in the second slide. I think that's in the real world, well, there's a continuous evaluation and validation of the approach. And another idea was voiced many times that if a doctor is not very good, well, yes, that one doctor may hurt some patients. If an algorithm that is in wide use is flawed in some respect, well, that's like it's like a medicine with strong side effects that come up, that may become apparent later, but they do much wider damage. And so the risk is much greater. As of now, there are, as of August, I believe there are, so that's the list of devices that have been approved by FDA. And in that paper, well, whoever has access to that paper, if you're interested, well, there are links to this device, and you can Google them. So there's a lot more information. Now the integration of patient health information at multiple interfaces. So in the end, well, it's digital healthcare. The center in the end is the patient, and so you have health information, then it goes to the patient. Well, then from patient information it goes to the healthcare system and payers. Well, I'm now part of Anthem, so I'm part of the payer in a company. And my view is that, well, the health insurance companies can be made, rather than gatekeepers for cost, right? I think they can be made partners in probably promoting and enabling efficient treatments. And again, the key, well, because there are many, there's information in many different areas. Well, standardization, storage, if you will, is critical for facilitation information exchange. And this FHIR protocol that's in place now and is being further developed is going to enable it to facilitate. That's just to mention. Well, I just downloaded and played a little bit with this app. It's a chatbot. It's a medical chatbot. Just will say whatever. Well, you have a cough. I tried it, and then it goes through a couple of intelligent questions, and then it tells you, okay, well, 1,000 people like you in this particular case did something with the cough suppressant. Or if you give some more more worrisome signs, it may tell, okay, well, most of the people like you with these conditions will went to see a doctor. You might do as well. It's not FDA approved. It's not medical device. It's one of the ways that kind of people can get in that space where you don't have to get FDA approval, because you're not dispensing medical advice. It's by analogy, and that actually is it's an interesting idea. There's another idea of there's a paper that says monitoring patients like monitor or analogy between monitoring jet engines and patients. And the idea is that, well, in the systems that monitor jet engines, there's a physical jet engine and there are sensors, there's all the data, but there's also a model running of that jet engine. And then, well, that model can help identify problems because it can simulate all the different conditions. And it can help to make a decision where to do maintenance, well, whether it's safe to fly or not. And the idea again is that, well, sometime in the future, if more medical information is available, then there could be quite a few people who have the exact same conditions as you are. And so that would become your kind of digital humans. And then, but these people may be, well, it could be similar genetic or makeup, or there could be so many similarities that whatever is happening to you, you can kind of you can use that information about other people as your digital kind of counterpart. So that's I don't think this is exactly true, but there is some truth to that. In particular, because most of academic papers are behind the paywall. So if you're in the university, you have access to academic literature. Well, that's great. But if you're in the industry, it may be hard to get, and that's unfortunate. So I don't know. Do we have? Yeah. So any questions? Yeah. Yes, please. Yes.
I think a lot of medical size. Now, when you're doing surgery, you have to distinguish between cancerous and non-cancerous tissue. It's not always clear. Maybe an artificial intelligence do that in their surgery. You know anything about medical AI application size?
Well, yes. So I just focused on diagnosis because the goal for that talk was just to give a little bit of to give at least some perception what I could understand what clinicians have. But what there is robotic surgery, and yes, you can think of with robotic surgery in particular. Well, when surgeon is looking at the screen, well, that same technology that well, in some sense, you can think about a gastroenterologist who is doing an endoscopy. That can be translated into robotic surgery. So it's the same thing. You get. It can help identify the boundaries of tissue that needs to be excised. Well, treatment plan, I don't know, because that would mean that that AI or deep learning, well, not necessarily deep learning, that AI would need to be based on essentially on HR data and medical records data, and plus whatever is available in medical literature. So I don't know. Potentially, you can think of that. That knowledge can be digitized and analyzed and then put into models, clinical models. But I don't know how far along we with this. Now, I didn't talk about monitoring at all. So there are wearables, and there are other wearables for health, and then there are wearables as diagnostic wearables that can be also intermittent or it can be continuous. So there is one of the FDA approved is Guardian systems that's continuous monitoring of glucose level by Medtronic. It's already in the place. Then EKG monitoring is essentially in place. Another is well, one of the problems I was told by a physician that there is a real drug epidemic in this country, and that well, people don't take prescribed drugs as required, and so anything that's behavioral intervention. So anything that can help with this would be another application. I didn't talk about mental health at all.
So, I think given the algorithm's ability to order tests, so if they look at a doctor, if he's not quite sure what it is, they can order a test. If the algorithm order tests, we will be like set up the amount of information that the algorithm can get. See if they
I could think that well, one of the decisions would be accompanied by a list of suggested tests. As of now, that would come under treatment plan, I think, or next steps. So it's although well, yes, it's part of the clinical decision making. And I would think yes. I haven't read about it, so I haven't seen any. Publications, peer review clinical publications on that.
I mean, that's the standard grounds for a physician. You have a group, and then they say, well, what would be the decision? It's not the way a doctor gets taught.
Yeah. Is there, yes.
Hi. I'm curious why. Curious why an insurance company, that's what Anthem
Yes.
is putting so much. Obviously, it's expensive. I'm trying to think of why, because you can't pick who your customer are. You can't have a cap on the cost. So it seems to me that you're going to be using AI to push doctors and hospitals to limit tests. And if they don't, you're going to put pressure on them, to push them out of their in-network tests. So I don't understand why an insurance company doing this work instead of like a hospital.
Doing this work meaning.
Your company actually has a fairly spotty record. It goes way back. You can have to change it. Even when you mentioned breast cancer, you turn down a lot of women who have breast cancer. You have to policy. Back in doing this work, and you can't actually do it. That's the pressure on the cost. And I think a lot of doctors want to do that test. They don't know they want to test. That's my question.
Yeah. So I have two choices. I can either punt it and say, well, I just joined Anthem, or I can try to answer. So let me can I speak not as an Anthem representative in any way, but just my personal view, and that is that in the end, well, whatever can be done is determined in very large respect by how much resources are available. So, well, obviously, it's if it helps to just to cover every possible kind of case or every possible hypothesis and get a test, well, sometimes it could be a better way. I don't know, but my understanding is that, well, insurance in the end is guided or should be guided by what's the best outcome. Because fundamentally, the best outcome, the healthier the people, the better it is for the insurance company as well. And so in this sense, AI, if it can help identify on a large scale the best treatments, not the cheapest one, but the most efficient and in a sense of outcomes. So clinicians talk about outcomes. And my hope in the end that, well, with AI, insurance companies will also think in terms of outcomes. Well, I think they are in terms of outcomes. But again, well, this is my personal.
Yeah, so I want you to talk about a little bit about, you talk about explainable AI, what in terms of like responsible AI. Instead of that, having the AI that actually tells you that this is actually, right or correct, like not being able to like somehow maybe, like for example, interpret something because maybe the image was somehow scanned or whatever was not done right. And then you get a different type of, diagnosis, a different type of outcome, which actually becomes maybe something that is lethal or something that is whatever that, for a particular patient. So has there been any type of, work and so you're going to try to ensure that whatever the AI algorithm produces or so that there is some type of verifiability, just testability to actually make sure that what it did was correct and it wasn't like, for example, maybe it was some spectacles inside an image or whatever that caused the AI algorithm to like be incorrect. So for example, you talked about like the self-driving car, and a lot of times for self-driving cars, if you somehow like manipulate some particular like image or you add some particular thing to that image, then it will think of something else. So then it will actually be fooled and then it will not detect or not give the right answer.
Right. So one sort of you can think of as insurance policy in this sense that, well, the clinician is involved. So you can think, well, if that's an image, then the clinician sees the image, and then the algorithm generates an assessment of that image with the probability of certain things, but clinician is still there. So in this sense, again, the view is not to make a self-driving digital doctor. The idea is to say, okay, well, if you're veering off your lane, then the steering wheel begins to vibrate, or just enable you a couple of different views. So this is one. Another is, and that's goes back to that question. So the idea is, well, how generalizable do you want to make that particular deep learning application? And the idea is that, well, if you use only the training data from that particular hospital with that particular equipment, then it may well be that, well, some features of that hospital and their equipment that are not relevant to this particular disease at all, or that condition, would be in some sense would affect the diagnosis, especially if that algorithm then is going to be used in another hospital. And that goes both ways. So if you want to have, you may want to have on the one hand highly generalizable algorithms. On the other hand, there could be something peculiar to that hospital, for example, that you would want to have the algorithm trained on, because that does affect the treatment and outcome. And so that's there is no single answer for that.
And the second part of that, do you think that for the next generation or the new generation of doctors who are in training or so, do they need to have some bit of knowledge in terms of machine learning and AI, and then be able to go ahead and say, oh, you know what, maybe that's not correct or whatever what it did or so. Like, there are need for new generation of doctors having to know some bit about AI or trying to, so not just blindly, just okay, this is what you gave me and that's it, but somehow like questioning and kind of understanding what the algorithm did or something. Well,
the short answer is yes. And my understanding is that, well, no doctor will just follow that suggestion of that algorithm. And actually the resistance is precisely because, if you get a suggestion and you don't know exactly how the algorithm came up with a suggestion, well, there is a strong resistance. And so that, yes, and there's quite a bit of kind of talk in the clinical community about educating doctors, all the way from the basics of what AI does to how to use it, in particular, what the shortcomings are. The benefits are kind of obvious. The focus, though, is on dangers and potential negative effects.
You have questions from the audience?
I wonder what your viewpoints are. You're a payer kind of with this vision of the AI platform with internal to you. What's your vision of the bigger digital players like Amazon, Microsoft that are launching their own ventures, like Amazon, Berkshire, Chase, they're forming their own sort of networks to sort of apply their AI and cloud strength. I was curious on you have any opinions on that?
Well, in some respect, that's going to that previous question. Why would the insurance company get into that space? Well, in some sense, precisely because Amazon and Google are going to the same space. So that's how healthcare is going to be transformed, whether Anthem wants it or not. And so, Anthem is just going to the same think of it the same activity, the same space from a different kind of point. But it's pretty clear that that's how medicine is going to be in the future. I don't know how fast, but it's obvious. Yes.
So are you aware of any effort? You mentioned the computer. Are you aware of any effort to work on something like that platform? Can you all healthcare or hospital? The AI.
No, I'm not aware. I think that for that platform to appear, there should be a pretty good infrastructure for data sharing access. And without it, you can't really build anything. So that's where the push is right now.
So the regulation for data sharing is hindering the AI development.
Mm-hmm.
Define that one.
Yes. So there is I think there's an international data repository with data for 1.5 billion records, something like that. There's a UK biobank. There's in the US. Well, there's a couple of repositories. So yes, well, one of the issues with data sharing is that it has to be, on the one hand, it's private. So for analysis, it has to be made non-identifiable. And there actually, and there is some research effort now is to see whether the data that is claimed to be non-identifiable is really non-identifiable. And deep learning is used for that as well, just to test whether it's true.
Always, privacy and the message.
Right. So if the question is whether there is some effort in that direction, well, yes, of course. How far is it? It changes. Well, it changes fast. So, yes.
Well, the privacy issue, that's solved with models, right? If you have a model, you don't care, you can't find out whose data was used to train the model, right? Especially if you get more than one person. You get thousands, millions. So that's kind of the solution to the privacy issue, right?
Well, no, that's the solution. Well, right. Private information is not coded in the weights. So if you share a model, then well, it's just a weight. So there is no private. But to give access to that data for to people who are going to train that network, that's where this privacy issue is.
So that's layers in the network, then, right? You remove the feature, you reduce the number of connections to the point where there's no likelihood of going back to determining the upper layer is reduced to virtually zero. And then that can be those layers, the weights of those layers can be shared.
This is going one step further from the data access and data privacy issue. So that's the step where you have the data, and then the question of how you train the network, right? But the issue is arises in the very beginning. If you want to train a model, you need to get some data. That data has to be de-identified, and so now the more varied the data, the easier it is potentially to identify whoever it might belong to. Now, not for the purpose of training. Now we're talking about some use of that data that's not intended. But this is the issue of privacy, protection. I don't know if so deep learning or not, well, the algorithm per se is not relevant to that question of de-identification of the data in the first place. So it's relevant for sharing, kind of for data sharing that information. Well, obviously, the more data is available about that particular patient that developed a particular condition, the more features you put in that data set, the more accurate in the end, I think the classification results are going to be. But then the trade-off again, well, the more features about the particular person you put in, the easier potentially for somebody who doesn't, who has no business doing it to identify that the patient.
Any last questions? No question about the OpenD. I mean, like if I do some research about the regular image recognition and use the data like image name, whatever, a lot of open data.
Mm-hmm.
For the medical data, I guess, are for the recognition data.
there are de-identified data sets, and actually for that paper from Andrew Ng's group on EKG recognition, they said that the data is available. The data is available. One part of the data is not, either data for training or data for testing. Data for testing probably is not available. I think the data for training is available, and that because, well, it's proprietary. Well, they're working with a company obviously who is making that product for EKG monitoring. But in many cases, that data can be available for research purposes, but not for commercial, which is fair. And so the suggestion is, well, if very often, especially in clinical journals, and especially in journals like Nature Group, code and data should be either available or available in request. So there is quite a bit of opportunity to reproduce these results and maybe use them in other ways. Plus, there are open databases with de-identified data. So that exists.
Okay, so with that, on behalf of ACM Chicago, we'd like to thank Mark Shapiro from Anthem to come today to talk about AI in healthcare. So I hope you guys got something worth out of this. So thank you, Mark.